Good morning, Evan.
Morning, Sean.
And good morning, everybody, and welcome to our webinar series hosted by yours truly, Enercon Engineering, Integrated Defense Solutions Business Unit, or IDS for short. Today, we're going to be discussing electromagnetic interference and tactical packages. I am your host, Sean Lott. I am the Director of Business Development for Enercon IDS. This is our third webinar in our 2020 series. If you missed the first two, the importance of power integration solutions and how specific requirements impact cost and delivery, I put those links to both of them in the chat box. Before we get started, you can ask questions during the presentation by clicking the Q&A tab located on the Zoom toolbar at the bottom or the top of your screen. We will discuss all questions after the presentation portion is complete. As a reminder, this session is being streamed live on Facebook at Enercon Engineering, as well as being recorded for on-demand viewing at a later date. Now I'd like to introduce today's presenter, Evan Ruha. Evan is the Chief Engineer for IDS. Evan has executed hundreds of jobs supporting commercial, U.S. domestic, and international projects over his 21 years at Enercon. To note, Evan was the lead engineer for the design of the Prime Power Unit, or PPU, in support of Raytheon's THAAD radar contract with the Missile Defense Agency. So with that said, good morning again, Evan, and over to you.
Thanks, Sean. I appreciate it. As Sean said, I am Evan Ruha, and today we're going to talk about electromagnetic interference and tactical packages. So the first thing we really want to talk about before we get into the actual electromagnetic interference in the tactical package is kind of what is electromagnetic interference? What is EMI? EMI is the interference of one electrical source or device with another by the means of electromagnetic fields created during its operation or by some other occurrence. Sources can be electrical devices or subcomponents within an electrical device, or even natural phenomena. It can be caused by the circuitry inside of those electronics, switching of large currents, electrostatic discharge, lightning, solar flares, auroras, or even intentional sources such as EMP. So how does the EMI get to the affected device? How does it get there? EMI is transferred in three main ways. The first of those is radiation, where the energy goes through space without necessarily any kind of physical medium to go through. The second way would be conduction, and that's through a direct conduit, a direct physical conductor of some kind. And the third way, there are actually kind of two subcategories of it, is coupling. The first of those is magnetic coupling, and that's when a varying magnetic field induces a current in the affected device. And the other way would be in a capacitive sort of coupling, and that would be through like an electrostatic means. All right, so now that we know just a little bit more about what EMI is, we need to think about it in a tactical sense. What do we protect from EMI, and why do we do that? So within our systems, the devices that are most susceptible to disruption from some kind of EMI would be communications devices, any kind of controller that we have, be it engine controllers or variable frequency drives, things like that, displays, and any kind of signaling or metering device. When those devices are operating, the EMI can really cause havoc. It can interrupt, degrade, change, or totally obstruct the signals that are carried to, from, and within those devices. And it can even, in some cases, cause physical damage. So in a tactical situation, any kind of degradation of performance, any of these devices have decreased performance or failure, and can have disastrous consequences during the battle. So how do we do it? At Enercon IDS, we typically utilize a multi-layered approach. The first layer of defense we have against EMI is a sort of external conductive housing, a Faraday shield of sorts. And what this does is it helps to absorb and disperse the energy through a ground plane that we construct. So the parts of that housing, the external conductive housing, that's the first layer, the parts of that are kind of the outer enclosure. And then clearly we have to be able to get in and maintain the equipment inside the enclosure. So there are doorways, there are penetrations for piping, there are penetrations for cabling, other electrical connections. And then typically we have air intakes, as a lot of the integration work that we do is for power. And so there's a diesel engine or a gasoline engine or some other kind of air breathing power producing device inside there. So we have to be able to get air into that. So inside the external housing, there are often devices that are more sensitive to interference. So we have to protect those with a little bit more, a second layer. So we use internal shielding. There are several different types of internal shielding we use, or different methods we use. One is to shield cabling. The second would be to, around those more sensitive devices, we would actually put a secondary housing. So an added layer, a second housing to help just disperse that energy that we would have. Again, typically that would be around control devices or control assemblies, anything more sensitive like that. And then the third way we can do it is use line filtering to protect incoming signals, power, etc. So pieces of the external protective housing, what we do, the measures we can take in that external section. Typically you would make it of a conductive material. Carbon steel is very good for this type of application. And then one of the most important things we have to do is make sure that we have a well-constructed common ground plane. So all of the housing has to be electrically connected very well so that we can disperse that energy. What we want to do is create a path for all of the interference and other negative energy to go straight to ground, as opposed to wanting to find a path through any of our equipment. One of the ways that we do that is when we do construct our ground plane, we make sure that there's no greater than a 2.5 milliohm resistance between any two interfaces. So between any two pieces of that outer enclosure, there can be no greater than 2.5 milliohms. And then for the ground plane itself as a whole, we make sure that there's no more than 5 milliohms resistance between any 2 points, any two electrical points in that system, no more than a 5 milliohm resistance. We talked a little bit earlier about having to be able to get in and out of the enclosure. So we use doors for that. Typically, we would make sure that those doors, when they're closed for operation, are sealed and grounded. So a couple of ways that we make sure that that happened is we make sure that there is a conductive seal that's both bonded to the door itself and to the frame. So typically, because doors have to be able to seal weather out as well as the EMI, we would use a compressive gasket, a conductive gasket, and we would adhere that to the door using a conductive adhesive. That's only one side of the equation. In order to make sure that we're maintaining that 2.5 milliohm resistance between the door and the enclosure, we also have to make sure that we treat the frame that the door would seat to as well. So typically we would do that by making sure that there's a very conductive surface there. Now, one of the challenges you run into when you're trying to maintain a conductive surface in a tactical unit is that you're outside. Things tend to corrode, they get dirty. To make sure that that surface that the gasket is interfacing in the door stays conductive, we typically like to use something like a metallized spray. We most often use tin over molybdenum, easy to clean, stays conductive, and it's durable. So that maintains the conductivity from gasket to enclosure and make sure we maintain that minimum 2.5 milliohm resistance. We also spoke earlier about having to be able to treat air intakes. Multiple things are involved in the air intake. We have to protect against weather. We also have to protect against the EMI. So typically we would use a weather protective louver, the frame of which is conductive. So we would use a similar type gasket metal spray surface that we would compress between the louver and the housing frame. And then the actual air path itself, we treat using a honeycomb gasket. These vary in construction. Typically for our applications, we're talking honeycomb vent that's 3/4 of an inch to an inch deep, and it has little honeycombs around 1/4 inch wide. And what these do, with the depth that they are and the fact that they're made of a very conductive material, we make sure that those, what they do is they capture the electromagnetic interference energy and while they let the air through. And then to make sure that those assemblies maintain that ground plane that we talked about, we sometimes have to supplement the gasket that we're using to make that interface with something called the ground strap. Now, ground straps are very specifically designed. The length to width ratio is carefully maintained to make sure that the strap itself does not become an antenna that would focus the EMI instead of dispersing it. And then we make sure that we connect those grounding straps from the frame or the honeycomb vent through into the ground plane of the enclosure itself. So that maintains that minimum or the maximum resistance of 2.5 milliohms. One piece of protection, or one method of protection that we use both internally and externally, is protecting our cables and our cable terminations. There are specific types of connector that you would use in an EMI type situation. The D38999 family is excellent for this type of application for both terminating your cables and your cable shields and for making connections to pieces of equipment and other cables. So D38999 type of connector, what those do is allow your cable shields to be terminated at each end to those connectors to maintain your ground. You were able to do a full 360-degree termination of the shield. So this doesn't leave any gaps that would let any of the EMI in into that cable or to that piece of equipment. And it ensures continuity to your ground plane by the fact that the connectors themselves have integral grounds that ground into either your piece of equipment, which then goes into your ground plane, or you're able to take a drain wire off of those and connect straight into your ground plane. The cables are also very specialized. In our applications, we tend to use a double layered braided shield, and it's an overbraid that is kind of wound counter to itself, so they overlap in opposite directions. And we would typically specify an optical coverage of 90% or more, just to make sure that we have the coverage we need to get the shielding we need to protect our equipment. Those internal components that we talked about, all the controls and the electronics and the meters, often the protection offered by our external housing isn't enough. So we have to add some supplementary protection to those just to make sure that their operations are not interrupted. So the construction of these cases is very similar to the external housing. It's basically a Faraday cage that captures and absorbs that harmful EMI and then disperses it down through our ground. Another thing that we often have to do, not all of the bad energy that we need to protect against, not all of the EMI comes from outside of our unit. Sometimes we have electronics and other things inside that actually can emit disruptive signals. So sometimes these secondary housings are actually to keep energy in as opposed to keep it out. So typically similar construction, and you would have the same type of ground and dispersion methods that we use for the other things, but in these cases, it's meant to keep the devices from disrupting operations of the other different types of controls and things we have, as opposed to keep bad energy out. And as we spoke before, ground straps are used to maintain the ground plane between many of these devices. A lot of times the casings, the way that they mount into your assembly don't give you that good conductivity to ground, so you need to supplement that with a ground strap. So oftentimes those have their own ground straps, taking them to a grounding point somewhere on the enclosure. Kind of the last line of defense, the last type of mitigation that we use are line filters. So there are places that we can't protect everything when we're trying to put together an enclosure. Cabling that runs outside of our enclosures is one good way to do it. One good example of that. So in the event that we can't fully protect that cable, can't protect that signal outside of our enclosure, we want to make sure that we protect it as it comes in. So we'll put a line filter in line that'll clean up any errant energy that would try to come in or any issues that would come in on that signal. Again, some examples of that would be bringing it from outside into the enclosure, or if there are certain zones within the enclosure itself that are not protected or less well protected, we would filter those signals coming in to the more protected areas or into the equipment. So just to kind of recap all that we talked about, I know we went a little bit fast through that. To recap, we do use a multi-layered approach. First line of defense is that external housing, and it provides protection to all the components within the main structure. And we do treat all the interfaces and penetrations to make sure that we maintain that level of protection. And those that we talked about were the doors, any kind of piping or electrical penetrations, and then of course the air inlets. Some components are more sensitive. For those more sensitive components, we do add additional layers of protection, external housings or extra housings over them. Make sure that we shield all of our cables, carrying signals, carrying power inside, any kind of potential conduit to bring in that negative energy. And then finally, we do use ground straps throughout the entire structure to maintain that consistent ground plane. Again, no more than 5 milliohms resistance between any 2 points in the system, and no more than 2.5 milliohms resistance between any 2 interfacing pieces of that system.
Well, thank you, Evan, for all your insights and your expertise on how to prevent EMI and tactical packages. We do have a few questions, and there's still time to submit questions if you would like. So it's not too late. So in order to submit a question, just click the Q&A tab located at the bottom or top of your screen, and I will review it, and we'll see if we can't get those answered for you guys. So Evan, first question. It's dealing with cost and expense. So how expensive are these EMI treatments that you discussed?
That'll vary. Depends on what the program is, what equipment you have within that program, and then the level of protection that's going to be required for it. We have had varying costs. It can be very expensive, depending upon all the things I just mentioned. We've actually had a few programs where the EMI treatment itself, between the engineering costs and procurement and production cost, it actually totaled somewhere around 40% of the total cost of the program. So it can range from fairly simple to quite expensive.
Wow, 40%. So are there ways to decrease the financial impact for EMI protection?
Sure. So one of the things that is very helpful when you're taking on a program that has EMI requirements is knowing those requirements up front. If you know the requirements up front, you can actually set up the way that your system is designed to cluster your devices that need the most protection together in a certain area, and then cluster the ones that need less in another area. By doing that, you can provide less protection to the pieces that need less protection, and that's of course cheaper. You don't have to put as much in line, and then you provide the higher level of protection only to those devices that you need, and we call that a zoned way to do this. So by segregating the pieces that need less, you don't protect them as much, and then you spend less money on protecting those pieces. Whereas if you weren't to do that type of thing and you kind of scattered your devices all over your structure, then you would have to protect all of it to the highest level, and that is more expensive. So with a little bit of knowledge up front in terms of what your program entails, you can do mitigations such as that.
So it sounds like to me, with each project, there needs to be basically a customized solution in order to meet the customer's needs and concerns when it comes to EMI protections. Okay, our next question is dealing with the time. So when you add EMI protection, does it add any time to the development or the project build cycle?
It really can, yes. The majority of the added time in terms of the project cycle, there would be some time up front where you would have additional engineering time to, say, set up and create your zoned way of setting up your structure. And then oftentimes procurement time for specialty EMI devices or specialty EMI products, such as the cables or the honeycomb screens we talked about, or those gaskets, all of those have a longer procurement time when it comes to being able to get them in-house to start your build. So it really can add time in those regards.
Okay. And we have another question here. It's dealing with EMI shielding itself of a package. So how do you verify its effectiveness? How do you know that it's doing what it's intended to do once you pin in all these protection measures?
That's a great question, actually. Validation of EMI shielding can be very complicated. It can be very expensive. Testing of systems such as these, it typically requires a lot of specialized equipment. It also requires someone with a lot of knowledge on the product and on the EMI type of science itself. Typically, a subject matter expert would be involved in this. So lead times to get that specified equipment available and to make sure that the personnel are available. Both of those things take time and can be expensive in that regard. And then to get the actual testing itself, there are multiple ways to do it. Typically, you would actually set it up kind of reverse of how you would intend the system to be used. You would actually generate your signal from inside the enclosure itself, and then test how much of the signal came out. It's simpler to do that because of the power requirements involved and the cabling involved to do it. You can actually set it up in certain zones and then test very specifically if certain interfaces are working correctly. You can test as much or as little as you think necessary. Typically on a program, we'll do very heavy testing up front. Once we've validated the design and the interfaces, then you can cut back on the specific interface by interface testing. But in the beginning, you test every interface to make sure that it's working as you designed it to.
I see. So let me see if we have any more questions here. So how do you determine, let me move this out of the way. So how do you determine the length and the width of the honeycomb air filter or waveguide?
There are a few things that go into that. The first thing you have to do is determine what your airflow requirements are. So in our applications, typically you have combustion air and you have cooling air. So you have to determine what the total airflow requirement is. And that can be based on temperature that you have to be able to have your equipment operate in has a lot to do with that. Once you've got your airflow requirements set, then you can go ahead and try and figure out what your overall area needs to be of both your intake louvers, which again are the weather protective piece, and for the honeycomb, because there's a resistance that is involved for the airflow to go through those components. So what you have to do is make sure that you have sufficient area to not restrict that airflow to get into your enclosure so that you can have that combustion air and that cooling air that you need. If you put too little area in, then you'll restrict the airflow too much and you'll fail out on an over temperature or starving the engine or whatever it may be of its airflow. And then on the other side, if you go too big, you're just adding cost into the system where it isn't necessary. So you want to find the balance between cost and necessity in terms of your airflow. So the size basically comes from that.
Oh, go ahead. We lose you?
Nope.
Okay. I thought you were saying something else. Okay. We do have another question. It's tied to the testing the effectiveness of the EMI shielding. So is there a way that you can simulate EMI or EMP source to do the testing?
You can. There are signal generators that you can use. Basically, I ran through it pretty quick in terms of our previous testing. You would use a signal generator inside the enclosure. That's one of the specialty pieces of equipment that I was talking about. To go back to that just a little bit, the three main types of things that you would use in that testing are antennas, and that's either a shielded loop or a dipole antenna. You would use a signal generator, and then you would use a spectrum analyzer to see kind of where your leaks, what frequencies, and what modes those leaks are in, or where the energy that is coming out is from.
Okay. All right. And we have one more question coming in. Let's see here. So the question reads, can these enclosures be dismantled for access to the equipment inside? If so, is there guidance on how parts must be reassembled to ensure the bond?
The short answer to that is yes. um, One of the things that's very important in EMI shielding is to make sure you have a consistent pressure across all of your interfaces. So much like when you're putting a tire back on, there's a sequence of tightening to make sure that you get all of your, let's just use an EMI vent, for instance. So let's say you have a 2 foot by 2 foot EMI vent. Typically, we would space fasteners for this EMI vent every 4 to 6 inches just to make sure that we had a constant pressure. And then you would, just like tightening a tire back, you kind of go in a crisscross pattern to make sure you tighten it down evenly all the way across and don't bind it up. So those type of things can be done. Instructing people on how to do that, you can certainly write any kind of manual you want. Going back to that, typically we like to try and not remove things like EMI screens and use doors and access panels. But when it comes to those type of access points, we use the same kind of thing. We need to make sure that we have latches, catches, or fasteners spaced evenly around to make sure that the seal is correct. On a door, it would be, instead of using, say, a single point latch, you would use a 3-point or a 4-point latch to make sure that you get consistent pressure all the way around the door frame. But yeah, you can certainly do those things for access, and you can certainly provide instructions as to how to take it apart properly and then how to reassemble it properly to maintain all your seals. The other thing that I would mention in that is anytime you take apart a joint like that, you need to make sure that you clean all of the interfaces, both the gasket side and the interface to the enclosure or whatever else may be it the louvers or the enclosure itself or the door frames. You want to make sure that you clean all of those surfaces very well before reassembling to make sure that you still have that conductivity.
Okay. Yeah, our next question deals with frequency. Do you know what the most troublesome frequency is to prevent EMI issues?
You're getting to the limits of my knowledge on this one.
Yeah.
I can certainly find out, but if memory serves me correctly, as you get higher in frequency, I believe the ones that we typically work in are the I better not say because I'm not 100% certain. I know that the higher that you go, you start getting into the 2 to 10 gigahertz. It starts to be a much more troublesome frequency. I couldn't tell you exactly what they are, but I can certainly get that information and we can get back to whoever it is.
Okay. And then the next one, it may require us to get back with this individual as well, is dealing with the mil spec. So what mil spec did we use to design for EMI?
I can actually tell you that one. Typically,
Okay.
the testing, the attenuation and testing requirements are typically carried in mil standard 461. So that's what we would use for guidance on the majority of these things.
Okay. 461.
Yep.
And let me read this question. Okay, so you touched on this a little bit, so maybe you can expound on it just a little bit more. The question reads, does the need to use furrious materials to ensure shielding cause corrosion issues? It goes on to further expound that obviously painted surfaces don't bond electrically when connected. Don't these joints corrode?
That is where we would use things like flame spray, the metallized spray. So to back up to the first part of the question, the answer is yes. You can use a ferritic stainless, like a 410 stainless, but really the carbon does a better job in terms of the attenuation. So we tend to go that way, but it does introduce the issues of corrosion that you talked about. So what we would do is in those areas of interface, we would use that tin moly spray to help mitigate the effects of corrosion when exposed. It's, again, very important to maintain that level of conductivity and minimize the resistances between those. And the metallized spray does do a good job at that. But agreed, it is a concern that you have anytime you use any kind of carbon steel in an external type situation.
Okay, Evan, thank you. We'll wait like 20 seconds or so to see if there's any more questions that pop in. All right, I don't see any more questions. So what we're going to do is we're going to wrap up this webinar. So I just want to thank Evan for taking his time to share with his expertise and information. Also in your inbox, you're going to receive a link to a survey. So please take the time to fill out the survey. There's only 5 questions, so it'll take you all of about 2 to 3 minutes to give us some feedback on the webinar. And we actually use your feedback. We review them, we go over them, we publish it after action review, and we incorporate your feedback in order to make our subsequent webinars even better. Speaking of subsequent webinars, our next free webinar will be on August the 25th at 10 o'clock Central Daylight Time. We will discuss making your case. So making your case, proving conformation through the FAI process. So Evan, thanks again for your time and your information. And thank you all for attending, and thank you all for your great questions. And we wish you a great week. Take care.